Hello. On behalf of Alpha Omega team, today I would like to take a few minutes to talk about mesh quality criteria and their acceptable limits. Element quality criteria. For each element, there are different criterion that shows the quality of each element, and Ansys can measure them and recommends a certain limit. I should mention, different software measure these criteria differently, and even from problem to problem, it would be different. For example, if you are doing a CFD analysis, these criteria would have a different limit than if you are doing a mechanical analysis. Here, for the most part, we are going to talk about how Ansys Mechanical and Ansys Fluent will measure these criteria and what are the acceptable limits for those criteria. Now, what are those criteria? Element quality. The first one is warping angle and warping factor. The second one is aspect ratio. Skewness, orthogonal quality, element quality, parallel deviation, maximum corner angle, characteristic length, Jacobian ratio using mechanical APDL, using corner nodes, and using Gauss points. In this video, we are going to go over each and individual of these criterion, and we will see how in Ansys Fluent and Ansys Mechanical we can measure them and what are the acceptable limits for them. Now, first, let's talk about warping angle and warping factor. In this section, we are going to talk about the definition of warping angle and warping factor, how to calculate it, and what is the accepted limit. First, let's talk about the definition of warping angle. Defines how much a node is out of the plane that it should be, regardless of the shape of an element. As long as they are in one plane, the warping factor and the warping angle will be 0. Let's take a look at this picture. On the very top left, as you see, the 4 nodes of this quad element, they are all in one plane. So obviously, the warping factor and the warping angle for this element will be 0. And as we try to move one of the nodes, let's talk about the right node. If we start moving it, let's say in Z direction and move it up, the warping angle and the warping factor will not be 0 anymore. Now, what does warping angle mean? So let's say we have an element. We are going to name each node, each corner node of this element, A, B, C, and D. And as you can see, the node C is a little bit shifted in the vertical direction out of the plane of A, B, and D. Now, if I go ahead and connect node A to node C, then I have 2 planes. Plane A, D, and C, and plane A, B, and C. Each of these planes, they have a normal. And as you know, the angle between 2 planes can be measured by measuring the angle between 2 normals. So, if I can measure the angle between N3 and N4, then I have the angle between these 2 planes. Now, let's go ahead and connect the other 2 nodes together. Let's connect node B and D together. Now, we're going to have a plane A, B, and D, and another plane would be B, D, and C. And each of these planes, of course, are going to have a normal, and again, the angle between 2 planes is the angle between the normals. So if I have N1 and N2, the angle between these 2 is going to represent the angle between these 2 planes. Now, the warping angle is defined as the maximum of these 2 angles. So if I go ahead and create 2 possible planes in each element and measure the angle between the normals, the maximum angle is representing the warping angle. Note, warping angle and warping factor cannot be calculated for trial element, regardless of the order, and it is 0. Because from each 3 points, a plane can be fit, and there is no angle to be measured. This is pretty important. If you use other software other than Ansys, let's say HyperMesh, if you have a second order trial element, if you try to measure the warping, or as HyperMesh call it, warpage, it is going to show it 0. Now, here is the question. How can we measure warping angle for 3D elements? Well, the warping angle for 3D elements is the maximum angle of all calculated faces. So we're going to have 6 faces in cube, right? If we go ahead and measure the warping angle on each face, the maximum of all the angles is going to represent warping angle of an element. Any break element having all flat faces has a warping angle and warping factor of 0, which is pretty obvious. As you can see, here we have a perfect cube, and then we are going to start gradually twist this cube, and it is not going to be 0 anymore. Note, if warping angle and warping factor is 0, does not mean the element has a perfect shape. Let's say we have a pyramid element, and I start pushing the top node all the way down, and I put all 5 nodes in one plane. If you measure the warping angle, it's going to be 0. So basically, warping angle is telling me that this is in perfect shape, and all nodes are in one plane, which I know by how I calculated it here, it is not true. So warping angle is tricky to measure the quality of an element. So if it is 0, it doesn't mean necessarily we have a perfect element. Now, how can we calculate the warping angle or the warping factor of a pyramid or a tetrahedra element? The warping factor and warping angle for the element is the largest of warping factors computed for 6 quadrilateral faces of a break, 3 quadrilateral faces of a wedge, or 1 quadrilateral face of a pyramid. Now, mathematically, how can I calculate warping angle? Let me bring back the same element that I used in previous slide. I am going to name it A, B, C, and D, just like before. And A, B, C, and D can have any random coordinate system in space. It is one element. Let me go ahead and split this element into 2 set of planes. Plane number 1 and 2, and plane number 3 and 4. So plane number 1 has normal number 3, plane number 2 has normal number 4, and the angle between these two is going to represent the angle between these 2 planes. And plane number 3 and 4, they're going to have normal number 1 and normal number 2 respectively, and the angle between these 2 planes, of course, is going to be represented by the angle between the normals. Now, we know each node is going to have their own x, y, and z. So for node A, we have XA, YA, ZA. For node B, we have XB, YB, ZB. For node C, we have XC, YC, ZC. And for node D, we have XD, YD, and ZD. In this example, what I'm going to do is I am going to measure the angle between N3 and N4. Basically, the normal of plane 1 and the normal of plane 2. So, for having the normal of each plane, we know since we have the components of each node, we can have 2 vectors. We can have vector AB and vector AC. And vector AB and AC can be calculated by subtracting XA xb, ya, yb, za, and zb. And same for vector AC, we can have xa minus xc, xa minus xc, and za minus zc. Now, as we talked about the mathematical, we know N3 is perpendicular to AB and AC. Basically, the cross product of AB and AC is going to be perpendicular to this plane. And if we call each component of that vector, in let's say in this case N3, A, B, and C, we need to have the unit vector of that. So for calculating the unit vector, we're going to have A over by root square of A powered by 2 plus B powered by 2 plus C powered by 2. And if we have the same formula for B and C, then we can have the unit vector that is perpendicular to AB and AC. Now, these three we know can form a plane. In this case, we call it AX1 multiplied by X minus X0 plus BY1 multiplied by Y minus Y0 plus CZ1 multiplied by Z minus Z0 equals 0. Now, if we do the same process and we have the cross product of AD and DC and we have the unit vector of N4, the angle between N3 and N4 can be calculated using the dot formula, which N3 dot N4 over the magnitude of N3 multiplied by the magnitude of N4 is going to give us the cosine of the angle between these two. And if we do the same process for plane number 3 and plane number 4 and measure the angle between these two planes, the maximum angle of these two is going to represent warping angle. Now, let's talk about how to calculate warping factor. If we have an element, as you can see, the blue lines are representing our element, and we are gonna name each node A, B, C, and D. Then the warping factor can be defined as 2 multiplied by H over by the root square of area A prime, B prime, C prime, and D prime. And H is A and A prime. Basically, A prime, B prime, C prime, and D prime are the average plane that node A, B, C, and D can make. So we know each node, A, B, C, and D, each of them, they have their own components, X, Y, and Z, with the indices A, B, C, and D. So let's go ahead and form two vectors, vector AC and vector BD. We know there would be a vector, let's call it P, with the component L, M, and N that is perpendicular to AC and BD. The reason that I am calculating vector P is, if I can have the equation of a plane that is going through node A and node C, and have another equation of a plane that is going through node B and node D, then I can go ahead and calculate the distance between those two planes. And having the distance between those two planes is going to give me 2h. And I know that the distance between node A and node A prime is going to give me h. And from there, I can go ahead and calculate A prime, B prime, C prime, and D prime's components respectively. So if vector P is perpendicular to AC and BD, then we know the dot product of AC dot P is going to be 0 and BD dot P is going to be 0. If we solve these two equations, we know we have three unknowns with two equations. That should be enough to form vector P, because what we care for the most part is the unit vector. So then we're going to have a relation between L, M, and N, which L over A is going to be equal M over B, and is going to be equal N over C. So if I go ahead and divide A by the root square of A powered by 2 plus B powered by 2 plus C powered by 2, then I'm going to have my first component. Doing the same thing for the second component, using B is going to give me M, and the third one is going to give me N. Now, I can have two planes. A plane that can go through A and C, and a plane that can go through B and D. And as we know, the general standard formula for any plane, for that we need a normal and a node, or a point in space. So for the first one, we have L, M, and N as the normal for the plane, and XA, YA, and ZA. And for the second plane, we have L, M, and N again, and node B with XB, YB, and ZB. So the distance between these two planes is going to give me 2h. Now, for measuring a distance between two planes, what we need is one node and the formula of the plane. So in this case, let's say I have XA, and I already formed the plane that is going through A second, B, C second, and D. So what I need to do is I need to just substitute my node to the plane formula and basically form the ratio over root square of A powered by 2 plus B powered by 2 plus C powered by 2. Now, this is pretty important. Now that we have H, how can we have the actual A prime, B prime, and C prime? Well, let's call X, Y, and Z for the A prime, X A prime, Y A prime, and Z A prime. We know the distance between A and A prime is going to be formed by root square of X A prime minus X A powered by 2 plus Y A prime minus Y A powered by 2 plus Z A prime minus Z A powered by 2 is going to be H. Now, we know that X A prime minus X A over H is going to give us L. And Y A prime minus Y A over H is going to give us M. And Z A prime minus Z A over H is going to give us N. So from these three equations, we can have our X A prime, Y A prime, and Z A prime. And we need to do the same process to measure X, Y, and Z for B prime, C prime, and D prime. And once we have that, basically we have each node of our projected or average plane. Now, how can we calculate the area of A prime, B prime, C prime, and D prime? Well, a simple way is to use the cross rule, which is the magnitude of A prime, B prime multiplied by the magnitude of A prime, D prime multiplied by the sinus of the angle between these two vectors over by 2, and doing the same thing for C prime, B prime, and C prime, D prime, and the summation of these two is going to give us the area of A prime, B prime, C prime, and D prime. It is important to know Warping angle and warping factor, they are both representing the same concept using different methods and basically different scale. Warping angle is in the form of an angle, and warping factor is in the form of a factor that doesn't have any unit. It's just a number, which is great. Then we would have a better sense if an element is close to ideal form and shape. Now, we know ideal value of warping angle is 0, and as we talked about it, ideal value of warping factor is 0 as well. So if we look at this picture, you see that the warping factor of the top left quad element is basically 0. And if I start slowly shifting the right node in the vertical direction, the warping factor is going to change. The first one is 0.01, the second one is 0.04, 0.1, 1, and 5. I'm sure you don't feel enjoying looking at having the warping factor 5. And of course, during the process of your solution in your model, you're going to face some issues of having accurate result, and sometimes your run may not even go through. So warping of 0.1 is visible given the flat reference, but seems trivial. However, it is well beyond the error limit for a membrane shell. Warping of 1 is visually unappealing. This is the error limit for the most shells. Warping beyond 1 would appear to be obviously unacceptable. However, shell permits even this much distortion. Furthermore, the warping factor calculation seems to peak at about 7. Moving the node further off the original plane, even by much larger distances than shown here, does not further increase the warping factor for this geometry. Users are cautioned that manually increasing the error limit beyond its default of 5 for these elements could mean no real limit on element distortion. Now, here is a table that Ansys is offering in its help. And it's for different types of element. For example, let's go ahead and look at the last 2 rows. Basically, it is saying that warning for 3D solid element quadrilateral face is 0.2, and same as above, the error limit is 0.4. And it's basically saying that the 0.4 is representing and corresponding to about 45-degree rotation, and 0.2 is showing 22.5. So giving this table and being able to calculate warping factor and warping angle, what is the recommended warping factor and warping angle? It really depends. It really depends to your simulation. It really depends if you are using it for CFD or mechanical. It depends to a lot of things. But as a rule of thumb, let's keep the warping factor less than 0.4 and the warping angle less than 45. Of course, in different simulations, in different problems, this can vary. Just my suggestion to you is try to avoid having more than 0.4 or 45 degree in the area of interest. With that being said, that was a wrap to explanation of warping angle and warping factor. Please check out other videos of element quality. I'm sure you're going to find some interesting content regarding element quality and its acceptable limit. Thank you for paying attention to this video. Please subscribe to our YouTube channel for further videos. Thanks for watching our video and hope you enjoyed it. Please make sure to subscribe to our YouTube channel for more videos.